Welcome back, everyone, to our last lesson on energy. Today we're going to be learning about the work-energy relationship, and we've talked about this a little bit so far, relating work to a change in potential energy or to a change in kinetic energy, depending on how we are looking at a particular situation. The work done can be related to the change in potential or kinetic energy, or equal to the change in energy as a total. So getting into this, if we, as we have done all year, don't consider any friction, any work that's done to lift an object to a new height is going to be equal to how much potential energy the object gains. It's equal to the object's increase in gravitational potential energy. And we abbreviate that GPE for short. Now, we've looked at this a little bit so far and talked about it for sure when looking at how to use water and the work done and energy released as we move water from a lower position to a higher position to store it for electricity production at a later time. So the change in potential energy only depends on the change in height. And it doesn't matter on the path taken as long as there's no friction. This is a key here. So when work is done against a force that's independent of the path taken, it's what we call a conservative force. For example, gravity and elastic force of a spring. For these two examples, it doesn't matter the path that we take, the change in potential is going to be the same. And I'll give you a little example here of a conservative force. If we consider a table that's, let's say, I don't know, 0.92 meters off the ground. If we wanted to move, let's assume that that is touching the floor here. If we wanted to move a 10-kilogram block to the top of the table, there are more than one route that we could take. I'm going to do this in a different color. We could go like that. We could go even higher. Bring it over, set it down. Or we could get fairly creative and put the book up to the top of the table. Since this is a conservative force that we're working against in gravity, it doesn't matter the path that we take. The potential energy gained by that 10-kilogram weight only has to do with the distance that we raise it off the ground. It doesn't matter the path that we take it. Air resistance and friction are examples of non-conservative forces. For these ones, the work done is dependent on the path taken. And if you think about that, if you were moving that 10 kilogram weight across a surface, or even just dealing with air resistance, the more you're moving that in more directions, the more air resistance you're going to experience, the more friction you're going to experience, which is therefore going to change the work being done. I'll give you a little example of this. Again, we'll use the floor and a tabletop. Again, we'll call this 0.92 meters. We'll take the same two 10 kilogram blocks, and we're going to put them on two different inclines. We're going to move one up to the table here, and we're going to move the other up to the table there. And that should work. It's not the best drawing I've done, but we'll call this A, and then we'll call this B. And I'll give you a second. You can pause the video and think about this. Which one do you think is going to require more force to move the same 10 kilogram mass up the incline? On A, it is going to experience more friction because that path is longer. The change in potential is the same. If we're going up 0.92 meters, and gravity is a conservative force, but non-conservative force and friction, that is going to depend on the path that we take. So sliding it on a longer ramp against friction is going to cause us to require us to do more work to overcome that friction. Now the force of friction, which we abbreviate F sub F, is going to be greater when the plane or the ramp is inclined at a smaller angle, because the normal force for the same object on the incline is larger, and the force of friction is equal to our mu times the normal force. So we're going to have a greater force of friction the flatter that ramp is, because more of our weight is acting downwards on that ramp. We're going to experience more friction, and therefore we're going to have to do more work against that friction. Now, conservation of energy. There is a law of conservation of energy that we learned about in chemistry, and we'll kind of rehash that here. Well, we got to look at this as a closed system. When we talk about conservation of energy, we have to look at it as a closed system where no energy is coming in, no energy is going out, which again is kind of a perfect world hypothetical scenario. So in a closed system, there are no external forces. I'm going to redraw that. There are no external forces doing work on the system. There's no external work. No external work being done by the system, and no transfer of energy into or out of the system. In a closed system, the sum of potential energy, kinetic energy, and internal energy always remains constant. And this is our E sub t. And the key point here is that this is in a closed system. We can transfer these types of energy from one type to another, but the total amount of energy in that system will always remain the same. It's simply going to take different forms and be transferred from one place or from one object to the other. This is all kind of summarized in the law of conservation of energy, which states that energy cannot be created or destroyed. Or in other words, the sum of the changes in energy, whether it's potential, kinetic, or internal, within a closed system is zero. Now the last thing we're going to take a look at today are a few different types of mechanical systems, specifically ideal and non-ideal mechanical systems. To start here, the total mechanical energy, when we talk about mechanical energy, it refers to the sum of the kinetic and potential energies in a system. So mechanical energy is referring to total kinetic and potential energy in the system. Otherwise, the total energy is going to allow us to do work. Now, an ideal mechanical system is a closed system in which no friction or any other non-conservative force because I don't need force twice, any non-conservative force acts. The sum of the kinetic and potential energies is constant, or the sum of the changes in kinetic and potential energy is zero. So net overall change would be zero. Now, two examples of this are the simple pendulum and an object falling freely in a vacuum. And we saw that when we watched a video of the bowling ball and the feather dropping in an ideal way, because we didn't have a non-conservative force such as air resistance acting on either the bowling ball or the feather. Now these energies can be expressed by the law of conservation of energy, which says the change in kinetic energy plus the change in potential energy is equal to zero, or the change in kinetic energy is equal to a negative change in potential energy, whereas both of these added together would equal zero. So as an object falls free from rest, we know the change in potential energy is due to a negative mg delta h, negative because we are in free fall, and the downwards direction would indicate a negative value. And kinetic energy is equal to 1/2 mv squared. Now as you gain kinetic energy and our velocity is increasing as we fall, that's why we have a negative potential because of our law of conservation of energy. Those two have to total up to zero. So we can also move this around a little bit and combine these together, and we can say that 1/2 mv squared minus mgh equals 0. Or 1/2 mv squared equals mg delta h, or mgh. Showing that our conversion between kinetic energy and potential energy is the same. Now, a non-ideal mechanical system is a system that is acted upon by a non-conservative force like friction. So friction causes a mechanical system to be non-ideal, or any other non-conservative force for that matter. Now, the total energy of an ideal system is given by the equation total energy equals potential energy plus kinetic energy plus internal energy. So ET represents the total energy in units of joules. PE is potential energy, again with energy going to be in joules. KE is kinetic energy in joules. And Q represents internal energy, otherwise known as thermal, again in the units of joules. So the key here in an ideal system, our change in kinetic and change in potential has to be equal to 0. Or the change in kinetic is equal to a negative change in potential. So what you want to make sure that you walk away with from today. I'm going to complete the example in class with everybody so we can work through that and see how this all kind of comes together. We'll work on that next time I see you guys. For today, I'll leave you with a joke. How do astronomers organize a party? They planets. Have a nice day, everyone.